Good afternoon, everyone. Welcome back for the afternoon session on faculty development program with the concept of advances in machine learning. So these 3 days we had a good number of sessions on machine learning with the different algorithm models and CNN techniques and data preprocessing optimizations and various versions of machine learning, various approaches of machine learning. So in continuation with the same rapport, today for the afternoon session we have Dr. PVV Kishore sir. He is a professor from Department of PCE, KL University. I would like to take the privilege to introduce PVV Kishore sir. Sir has received a master degree from Cochin University of Sciences and Technology, and a PhD degree awardee from Andhra University College of Engineering in the year 2013. He is currently a professor of image processing and video processing from Department of Electronics and Communication Engineering, KL University, where he manages the image, speech, and signal processing towards the gaps in the research. He also acts as a chair for the Biomechanics and Vision Computing Research Center. His work focuses on machine learning, biomechanics, artificial intelligence, human action analysis, and sign language machine learning translation. He is an enthusiast in developing new innovations in the areas of computer vision, machine learning areas. He has authored several publications in these fields. His research interests includes how motion capture data models can effectively with the low and video objects in real time for better recognition and analysis. With this small profile biography info, he had a good number of publications in various reputed SEI and Scopus indexed journals. Sir have a good interest in the publication areas, namely image motion analysis, image representation, video signal processing, feature extractions, image classification and recognition, object recognition, and sign language recognition techniques, computational geometric convolution neural networks, and the data asset management. So with this small introduction, we take a privilege to invite Dr. PVV Kishore sir for the afternoon session. Kishore sir.
Madam, shall I share the screen, madam?
Yes, sir. We will transfer the privileges. Just a moment, sir. Kindly check, sir. Privileges was transferred.
Yes, ma'am. Yes.
Thank you, sir.
Madam, is the screen visible?
Yes, sir. It is visible, sir.
Yeah.
And your voice is also clear, sir.
Yes, ma'am. Yeah. And good afternoon, everybody. And thank you, madam, for a big introduction. Actually, it's not a small, and I don't know how many things I'm handling currently at this point of time. So for today's talk, we'll have deep learning concepts we'll focus only on convolution neural networks and how we are trying to give vision to the machines, and I deconstruct the entire convolution neural network, how things go inside the machine and stuff like that. So let's start. And if you have any questions, if you want to interrupt me at any point of time, you are free to do that. So now, before going to that, let us see a small introduction on how I have learned all this stuff in last 3 or 4 years. So the 4 V's of big data, and these are not written by me. So it's given by a lot of educated people like from them, just borrowed this information. So for that, we have, so for big data, we have 4 V's that they regularly call it. So variety, volume, velocity, and veracity. So all these 4 things, and you can see here, there are quite a bit of challenges in first finding the data for a particular application. So once you have the data, it has to have these characteristics, and what are the challenges in various stuff, various processes that we go and build a data set. So that we build so many data sets where you can find that on our Yale University website in Biomechanics and Vision Computing Research Center, where we have freely given our 3D motion capture data sets for sign language, for yoga detection, yoga pose detection, for human action detection. Not only 3D, we have RGB data, and we have depth samples also, which we can just drop in a mail so that we can provide you the data. So it was challenging for us to build data sets, and what we observed in building those data sets was these 4 traits. We tried to incorporate all these things into our data set. So let us now, the data science process in general, these are the steps which we followed. So what are the different problems and what are the key steps in data science? So first one is classification problem. And once we have the problem for classification, so we'll focus mainly on classification, and now regression models will be shown to us today. So we'll take a say a image classification problem. Hopefully tomorrow morning we'll write code using TensorFlow and see how actually CNN does that. And then the second one is acquired data, and that is the biggest problem. So how you want to acquire data, and from the data should be very generalized. It should be structured or unstructured, so or else you can use somebody else's data set and stuff like that. That is data engineering. That is a big part in this current scenario, because the models have evolved to an extent like it is very little we can do with models, except like a big giants like Google or Facebook. Every week they give out like a new model. So except for those giants, the remaining people, the researchers who use machine learning algorithms, deep learning algorithms, they find little change in the structure of the deep learning machine. But the point is, the data should be data types, or like the data modulation is evolving day by day. So that is finding a suitable data set for a particular problem is a very challenging task nowadays, and there are so many people are working that. And then how to process the data. Those two, acquired data and processing the data, are the 2 biggest challenges now. So how you clean the data, normalize it, and how to divide that into classes. So that all that stuff. And then model problem. We have so many models for a variety of applications, but the point is the most of the models, they have the common structure of CNN, convolution neural network, or the recurrent neural networks. Most of them will be coming into these 2 categories. The structure remains almost same from last 6 to 8 years. So that there is no big change in that the structure. And then finally the big again, once we have all this, so we have to validate, and execution is a big problem, and then deploying is a biggest challenge. Now you have to know full stack development, front end, back end, for deploying your application online. So all these processes are there in data science, but we'll focus mainly on the deconstruction of convolution neural networks. So, and the life cycle of big data. Data science has three major components. So, first one is exploration and model prototyping. That is the job of the data scientist. So, if somebody who is looking for a job in data science, he has to have knowledge of all three areas. So, data plus model, machine learning, and how do you want to see your model when it is in production, when it is online. So how that model is going to perform, because the training data set is different. The inferencing that is happening at the production stage is it's completely different from the data that you have shown to your model. So that is the place where we have a lot of challenging tasks are built into that. So at the production stage, the deployment stage, and so all these three components, if have basic knowledge, and you can build on that. So that is what we are looking for. Somebody who is interested in building a career in data science should focus on. Now we have two different data processing models that are being operated. So for large data sets, but unfortunately, if you use a large data set, obviously the training process will be slow. So for that, we use batch processing. And then if it is a small data set like a text data set or what do you call the Excel type of data set, CSV files. So for that, we'll use stream processing. So you can just go through the different types, or so how much training time it takes. So all these things. So for today's talk, we'll focus mostly on batch processing, because we are going to deal with images and video data, which is huge, and it takes sometimes for us. Once we train our models on something like a 8 GB GPU, which takes around for a 1 GB data set, it takes around 46 hours, like that. So that is out. The size is, again, the size of the frame, the resolution of the image also matters. We are trained on 256 cross 256. So obviously, people who want faster training times, they can just scale down it to 128 cross 128 also. So this is the data processing. So how data processing evolved over a period of time in last few years. So first, Hadoop came in 2005 or 6 in that time. So you supply a query, and there are no GPUs at that time. And then the training time, as you can see, it is indicated. It's very large for small, even the small operations. So then Spark came in memory processing. They used that, and again, that was in 2008 or 9. And then the GPU, once the GPUs came into effect, we reduced the training times. The GPUs reduced the training times by quite a bit. And last 1 or 2 years, the NVIDIA is working on, like you can just see here, in the last, once a reading happens, GPU read, query, and CPU write, because the GPU cannot operate on its own. It has to transfer data from CPU to GPU in every batch for training. So, and again, take back those trained models, and again, it has to repeat the process. So what happens here is the NVIDIA is coming up where the CPU write can be removed. They're naming their machine learning library as Rapids. So it's in operational from last 1 year. So where the CPU write is removed from that, from the entire processing, and only entire machine operates on GPU for training. So that is what Rapids will do. So that is the latest one. So just to make you understand how the operation happens here, you can just see here. So it has to be a constant operation between CPU and GPU once you are loading the data onto the GPU. So CPU will, for every execution cycle, for every iteration, the data is copied from CPU to GPU and the results are copied back. So that is what happening. So that process they're trying to reduce, but the Rapids is not a fully evolved deep learning library. So again, this process is only used for simple ML programs. Now, these are the different open data science ecosystem that is available for you. So in that, pandas for analytics, sklearn from machine learning, like regression and other models, GMM and stuff like that. And for graphic analytics, we have NetworkX, but it's only 10 to 15% of the people use that. But most widely used is TensorFlow. Now PyTorch is getting from TensorFlow is from Google and PyTorch is from Facebook. PyTorch is getting popularity among researchers, but most of the industry that they follow TensorFlow because it's completely evolved library or API for deep learning models, and the MXNet is from Microsoft, which is still it has to gain some popularity. And for visualization, most of them use Matplotlib, but there are so many other components like other APIs that have come into existence in the last 1 or 2 years. But regularly, we focus on these things. So we use regularly these things to build our machine learning program, which we are going to see tomorrow morning. We'll write some code for CNN, and we'll see how it is good at classification of. We'll build a two-class classifier, and then we'll extend that. Now, why GPU accelerated times are very small compared to CPU? I got this figure from one of our friends, and can just see what are the CPU times and GPU times, how they are. They are trying to GPUs trying to reduce our training time by over 90%. So that is what does. So this is what the GPU has done. So why I prefer pandas, or there are so many other things also for loading the data into the Python. So I just can just see different data formats that are used in machine learning. So can just, but pandas APIs are very powerful, which are 10x faster than the other ones, which we have. It can be used to read all types of data types. So it is a simple Excel file or in JSON format, because most of the things now are in JSON format. So obviously pandas will do the very good job for data reading. And most we always get two types of APIs. One is GPU accelerated and other one is CPU ones. So you can, if you have a GPU on your machine, it's advisable to load GPU accelerated. So here from sklearn, we have so many things that we can do. So you can just see classification, regression, inferencing, and pre-processing for text and clustering, different time series validation. But it's done in ARIMA models, not in LSTM or recurrent neural networks. So, and then we can also do hyperparameter tuning, cross-validation. These are added lately in the last 1 year, cross-validation and hyperparameter tuning. Previously, they were unavailable in scikit-learn. Now, what are different algorithms for machine learning that are very popular. We have listed only popular algorithms here. So like decision trees, random forest, and regression models, nearest neighborhood processing, and support vector machines, and base classifier. So all that most widely used algorithms for machine learning. So all these are available in scikit-learn. And then the software infrastructure required to do all this stuff. C++ is most widely used, but obviously the most popular one is Python. So we have very popular frameworks from Facebook, PyTorch, Google TensorFlow, and CNTK from some other, I forgot the company name, but that is also, but it's gaining popularity, but most widely used. If you check what is the most popular API for building deep learning algorithms, it will be TensorFlow. So so it has all the SDKs. So for training, it is the best one. And for now, you have to you have to train your deep learning algorithms. You have to use on GPU. You have to use CodaX. It's a library which transforms all your code in Python onto the GPU. So it's a transformation. What do you call transformation? Transformer which transforms your Python code onto the GPU. So that is also required. So for transforming your code onto GPU. Now, which is built into TensorFlow 2.0 for GPU processing. So you can, when you are installing, so you have two versions of TensorFlow. One is from one is CPU accelerated, the other one is GPU accelerated. So while installing, again, once you install that, you have to also install CodaX AI libraries to have the operation. This to have a smooth operation between the Python APIs and the GPU. That is the story of GPU. Now, because I'm focused on using NVIDIA GPU from last few years, so I focus on that. So you can just see that here I have included NVIDIA Rapids. So that is the new library from NVIDIA, which tries to which minimizes the transfer between CPU and GPU. So that is, if you want, you can try out that. And different servers for real-time operations. We have TensorRT and Triton inference server, which are available. They're costly things. And then for cloud computing, what you have to use. For just for infrastructure, you can just go with vGPU. So it is they are very good. Or you can buy a Jetson Nano or Jetson, different varieties of Jetson for your operation, which is, they are external GPUs. They work fine in terms of handling small loads. So they come in different versions, 2 GB to 8 GB. Now, you obviously know all this stuff because you're going from last 2 days, and most of the audience, I know they're well educated in understanding the machine learning models. So we have classification, regression, and clustering, 3 types of generally machine learning models are classified into 3 types. So you all know that. So I'll just keep this. Now, examples for different machine learning models. We have logistic, Bayes, k-means, and all that. That's the most popular ones we have highlighted. So because they are faster, that is what the entire thing is, why they have been highlighted. They will do a decent job. They're not like the excellent algorithms, but they'll do decent jobs. They give more than 60 to 70% accuracy. but still they are really fast. Their operating speeds are very high, so that's why we have highlighted them. Now, for coming to human vision to machine vision, so how to transform that? So why humans? Once we have the vision, how it is used by the humans, and the same similar things can be incorporated into the machines or not. So that was the question that was asked, and maybe that is the basis for development of image processing some 50-60 years back. So generally for navigation, recognition, object handling, environment understanding, threat analysis, motion, it's emotion recognition, reading and writing, driving, and the list goes on. So 90% of our task, day-to-day tasks, are related to vision-based navigation. Can the same things, but with the vision, we have a powerful supercomputer sitting on top of every human being, which can process, I don't know how many bits per nanoseconds or stuff like that. The same thing can machines do. They are evolving, and it's a very good sign. Now, previously, most of the people they have done this automatic facial recognition. So it was most popular with CNNs. It has become most popular with CNNs now. Everywhere they use face recognition. Now, previously they used to get the face. How they used to make the data set? They used to get the face. They used to mark these points, as you have seen, and then extract features from those points, and then draw histograms or use some mathematical expressions on those features, like statistical parameters and stuff like that, and then use them for classification. So that was the previous, like 5-6 years back. If you want to develop a face recognizer before the evolution of deep learning, so this was the story. So you have to extract features and sorry for the disturbance, guys. That was the story before the evolution of deep learning. Now the deep learning has somewhat what do you call, it has reduced that effort to a bare minimum. So what is that effort? How it has done? We'll focus on that. So there are different types of feature extraction algorithms, LBP, binary features, and there's local binary patterns. There's Swift features and surf features. There are so many features which we used to use in around 2012 or 13. My PhD, I used so many different features. Now the task became how it became automated. So with the help of it started with the help of neural networks, which were there from around 70 years. So when I first started reading neural network book, the evolution started for artificial brain in way back in 1950s or 60s, and then unfortunately why it lost its popularity, because it needs huge amounts of classification, like calculations, and unfortunately till 2012 or 13 there were no big hardware available to process this kind of information. That's the reason why they were like they were not very popular with the organizations, with the industry, because but unfortunately it was there with the research. Now I used to train in 2008-9 on a CPU, same neural network for image classification tasks. It used to I have to extract features, and again I have to set up the data set, and then I give it for training for a small, like a 1 GB GPU, 1 GB CPU. It used to take around 30 hours for a normal neural network for training, with only something like 50 classes. So that was the issue then, but it's changed. So why? So the structure, if you can see here, the first input layer, it does nothing. It just absorbs all the inputs. And what they claim is in the first hidden layer, it will extract minor features like edges and small tiny components that are related to image. In the second, it will go for some of the objects and then object parts, and then the last layer, the second next hidden layer will have the uh, entire object. Here in the case, entire face for recognition. So that is what most, if you type CNN, if you type anything deep network, it will show this image. Now the question is, are they really learning edges? Are they really, if you can go deep and see inside the first layer, after the first layer, what will be the output, and is it clearly learning the exact, what do you call, the edges? And the second layer, it is learning objects. In the third layer, it is learning all the entire characteristics of the image. Is a big question. So that was the first time when we thought we got interested in understanding what really goes on inside those machines, inside those layers. So that was the first time we want to see exactly, are they really doing? We tried so many iterations. We have used, we try to reconstruct the what do you call, the intermediate layer outputs. So tomorrow I'll show you, and today also I'll show you. Tomorrow with the help of a program. Today we'll show you. We'll see what it is actually doing. So this is the basic structure. In the training phase, we have to give the training set. So you can just see the first set have different images of a particular person, and they all carry the same label. So his name, most probably in this case, the second set, the third set, and all that labels. So each of that you have to put in a folder with all the image names, and the folder carries the class label, and each image will come into the deep network, and it will learn with respect to the class labels. And then we have the loss functions, which will help the deep networks to learn. And most popular, the loss functions, the cross entropy loss, which is most popular in all the deep networks. And then we optimize the weight vectors using either gradient descent. That is how it learns gradient descent algorithm. The backpropagation stuff is learned. The error is learned using gradient descent algorithm. So that is the optimizer. And then in testing phase, you just have to give images to the network, and it will classify them. So that is the story of all deep networks, and for classification purposes. But you see the ANNs versus CNN, there's a small difference. You can just see here. Now that is the image, but for ANN, I cannot give an image. It has to be in the form of a vector. So feature vector. So the size of that image is 28 cross 28. So if you multiply, you will get 784 samples. So each pixel we should have one neuron that is sitting there in the network. So that is how it learns. That is how it happens. But you can just see the process. The loss is adjusted back to the weights. And actually, X1, X2 are getting also their blink, but they're not getting modified anyway. No, we don't modify what is there inside. Inside the neuron, it's only an activation function. It does nothing. So only it will decide whether the neuron has to fire or not. So the modification is done mainly on the weights. So weights and biases. So those are the only things that are changing during training. and remaining things will remain constant. So they are called hyperparameters. Now, if you see the CNN, this is the structure of CNN, where you can just see the input is an image, and the features are extracted in different layers, and the output again. See the convolution layers that they extract only features. They learn the extraction process, and at the end of any deep network, we will have again a fully connected layer which actually learns, like ANN at the end of CNNs or LSTM or RNN or any network. The last few layers are dense or ANN, which actually learn the entire feature. So the only thing is, previously we used to extract features and give it to the ANNs. Now the network will extract the features, and it will give that features to the uh, neural network for learning. So that is what is happening in CNN. So that is the difference. You can just see here, that is the basic operation of ANN. So this is what is learned, and the weight vectors are connected. Each neuron is associated with a weight vector. So that is what we are trying to modify. And at the end, when you say a train model, here we know that all the weights are trained according to the input and the class label. So that is finally we are what we are saving in the form of a trained model is a weight matrix and a bias matrix. That is what we are saving. So this is what happens in the inferencing stage or the testing phase, where you have the input and it gets multiplied with the weight vectors, and you'll have the output. So the inferencing or testing operation is quite fast. Means it is that is what makes it more interesting. Even though training takes a lot of time, the inferencing or the testing part is very fast. So that is how these things operate. That is how they have become popular. And so those who are interested for a mathematical background here, so you can see the output is the bias. Bias is like you can control the state of the neuron using the bias. You want to model a certain thing, like it's like pre-organizing. It means you know the certain things, and from there you are training. So for that, bias will be helpful very much. And then the weight matrix gets multiplied with the input vector X. And for most of the machine learning or deep learning algorithms, this is what is the output. So they mostly use accuracy or precision or recall or entire thing in the model using a matrix like this. It's called confusion matrix. You can just see here. So the actual test vector values and the predicted values of the network. So that is the confusion matrix, and how accurately it is doing, that is the accuracy. The total number of correctly recognized or correctly predicted samples by the total entire entire data in the test set. So that is accuracy, and the true positives will give recall, the true negatives will give precision. But most of this time, it is better if we can understand accuracy and draw this confusion matrix, which will accurately tell you how your test vectors are working, and how your network is performing under these testing conditions. Now let us talk a little bit about the mighty CNN. Now the CNN, you can just see here. Let me run this if it runs. Yeah, this is what is happening. These are the different layers. So one We have convolution layers, and the convolution layers are characterized by filters. So the number of filters you can suggest the network, how many filters you want, the size of the filter also you can suggest. Those are in your control. So how many filters you want, how many types, how many, what is the size of the filter, and then the second stage is pooling. Now, so many filters will give, suppose I have 10 filters on one image. So I'll get 10 outputs of the same resolution. So I want to reduce. So I cannot carry forward all the, because all the filters to the next stage. A part of the filter will do the job. That is what they identified, they discovered, and they used max pooling because most of them will be zeros. So by pooling the maximum numbers, it's just numbers. They are playing with the numbers, so it's the maximum numbers are selected and the minimum numbers are discarded. And if you use a 2x2 max pool, the entire size of the resolution of the image becomes half. Then ReLU is a activation function which will fire the neuron, which will say whether the positive samples should go forward and the negative samples should stay back. Then we have the second layer, we have same things. And then third layer, we have the same things. You can put any number of things. And once we do that, we have to flatten the, because it's a matrix size. It looks like a matrix, so I cannot give that matrix to a fully connected layer. So it just you have to flatten the matrix into a linear vector, and then you process that. Again, we have, you can put any number of linear layers, but two is the general thing. And then the softmax layer is a part of the dense layer, which gives the output classes, the probability of the class label that is most suitable for an input of 7. So softmax, the what we call that, the softmax will have a sigmoid function, which gives the output as probability. Then based on those probabilities and the maximum probability you'll select, which is equal to the input label. So here the label, that is what they're doing. They will match the output label that is generated and the exact input label. And if it generates an error, then it is used to train these weights. So that is what the CNN models will look. So for this is a model for image classification. As you can see, the dog input. Now you can just focus on the output of the softmax. Why it is represented in this particular figure? Because it gives the probability values of the input. So how the entire, if you add all the probabilities in the softmax layer, it comes to 1, and most of them they use the same dense layer with ReLU, but unfortunately the last layer is a dense layer with activation function as sigmoid or softmax. Both are same. So you can type in Google and check. Softmax and sigmoid both will have the same activation, the same expression, which takes input, which transforms all the inputs into a probability scores. You can just see. Now here the dog has been classified as the bright ones are which it's getting trained. So it is not training properly. That is what we can see here. Now, the face recognition is quite simple in using deep learning. The inferencing part is quite simple in deep learning. So this is what background deep learning algorithm is running. It's trained on a very small data set of 10 to 15 faces, each having only 10 variations, and still it performs very well. Maybe it's the face is very close to the camera, and we also done for detecting. This was very popular 1.5 years back. Everybody was doing deep learning with to detect COVID from the chest images. So that's we also tried. We got a data set from some Chinese university, and we tried on this model. This was the model we have built, and it gave 97.91 accuracy for the test images. But the image data set was very small. So like it has only 500 to 600 images in different classes. I'm saying the overall images were around 500. So the data set for of to make it as a real-time application, the data set is quite low. This is one more application where you can take a CT image and extract the parts from that. Now, the biggest where this all started, it started with ImageNet challenge from 2010 onwards. So about 2010, there were no deep learning algorithms. So the ImageNet challenge was given by Google. So you can just see the error at that point of time was 0.28, 28% on the test data set. And in 2017, they stopped because it was only 2%. So 2% is a very acceptable data set. It's still 2018 or 19. If you see, it has gone down by less than 1%. So that is it's the biggest. You can download the data set and you can try on your model. And from 2012 onwards, the first one was AlexNet. So this was the entire data set given by Google. It has 1 billion images from different with different class labels. So you can see all the class labels and stuff like that. So it has combination of inputs also. So how they have labeled it, I don't know, but they have done it. So it has a total 1,000 object classes and 1.2 training images and 100K test images. So it was, you can try when you are starting with this. We can try this. Now you can just see different models which have performed exceptionally well on that with top 1% accuracy. You can just see the first one was AlexNet. The first one from some Russian developed that first deep learning model, and then it transformed everything. And the latest one was Inception V4, which doesn't go deep, which expands parallelly. It's not vertical model. It goes vertically and horizontally also. The model expands. The architecture is quite complex. And if you want to run that on 8 GB GPU, it will take, for this data set, it took us around 76 hours to train the model, the Inception V4 model. But most popular were Inception V4. VGGs were very popular nowadays also. And then the ResNet is one more popular model. So GoogleNet again is Inception V2 model. And then all others they tried, but these are the popular models. Still 99% of the industry or researchers, they validate their research using this. Even though they have designed their own model, they validate their models using these standard architectures that were designed by so many people. Nowadays, so many other architectures they have stopped the challenge at this point of time. Now you can see the inception V4 have 155 million parameters, trainable parameters in the sense weights and biases. And now this is the structure of ImageNet for VGG16. We have 16 layers. The first two layers, you can just see we have written the frame size also, 224 cross 224 cross 64, because 64 filters are there of size 3, because all the filter sizes in VGGNet are constant. That is the beauty of VGGNet. So all others, they change. They use, sometimes they go for 5 cross 5 or 7 cross 7, 9. Some use 17 also. But maintaining a standard filter size across all layers, all convolution layers, you can exactly there we can see that it has performed exceptionally well for image classification task. So the input size is 224 cross 224 cross 3 for RGB values. Then 64 filters in first layer, 128 in second, 256 in third convolution layers. We have 3 layers. Then the red one is max pooling, which will slash the entire frame by half, because out of 4 values, it will select one maximum value. That is the idea of max pooling. Then we have 3 convolution layers in the third part, and then we have again max and 3 convolution layers, and then last again we have 3, and finally the entire 224 cross 224 gets reduced to 7 cross 7 into 512. So 512 filters we have, which are of size 7 cross 7. Then again to use that, I cannot give a 7 cross 7 to a dense layer, so we just have to reduce that. So if you multiply that, we'll get 1 cross 4. We just arrange the 7 cross 7 cross 512 into vector, into a single vector. We will get 1 cross 4096, and then you can do the. You need not have to use all the elements that are there, all the filter values that are available in the 7 cross 7. So you can just randomly remove some of them, because to induce non-linearity, because all these, they're completely, all operations, if you see, the mathematical operations are very much linear. So, but in real time, the machine learning or the artificial intelligence is all about understanding non-linearity. So to model non-linearity, they have introduced a dropout in the final layers, which randomly removes 50% of the samples from 50%, or whatever number you select will be removed from there. Or else you can directly reduce, like you select the dense layer only. Suppose if I select 1,000 here in this case, the dense layer number of neurons in the input of dense layer is restricted to 1,000. It will take only 1,000 inputs. Remaining inputs it will discard. So automatically non-linearity will be introduced into the network. So that is where the non-linearity comes in. That is the basis for artificial intelligence. That is what I have understood in last 3 or 4 years. Now this is a very deep model that was this was VGG16. The previous model which we have seen was VGG16. So it has 16 layers, and now this is ResNet, and you can see how deep it goes. It has, like, the only thing. The people who designed ResNet, they understood is, if we go deep, we can extract more number of features. So that is how they understood the things. But once they start going deep, you can just see the second middle one. there was like the difference between the top architecture and the middle architecture. The last one was VG16, which we have already seen. So we are not focusing on that. So you can just see the difference. Now the previous first they proposed ResNet 34 layer, the plain one, the middle one, where there were no interconnections from previous layers. So what happened is when you go so deep, once you hit a zero between somewhere between middle layers, and it gets multiplied in convolution, and all the values will become zero. So once it goes on like that, and in the end, most of the samples in the output will be zeros. So that is the problem is called vanishing gradient. So the entire thing, why it is called vanishing gradient? Because when you're doing back propagation in that, so zero is getting transmitted, and you're multiplying that with the weights. And unfortunately, when something gets multiplied, some value gets multiplied with weight as zero, so it becomes zero. So that's the problem. So what they did is, after every 2 layers, they thought, I will reinforce. This is a classic example of reinforcement learning, where I'll reinforce the feature vectors from the previous layers. So that is what they are doing here in the top model, which we also applied for so many applications, and it really works. It's like this is the basis for nowadays the transformers or multi-attention models that are very popular in they became popular in last 1 year with the coming up of transformers for text processing, speech processing, and nowadays they are used for image classification tasks also. So those are the stuff. This is the basis for that. So they reinforce the features every 2 layers, and just reinforcing in the sense they'll take the previous layers output and just multiply here with the output of the second layer. So that is how it goes, and it has solved the problem, and that's why they went from 34 layers to 101 layers. Some people, they use 150 layers, 200 layers, and more than that also. Now this is the inception. You can just see he has gone deep, and at the same time it has multiplied in like it has expanded horizontally also. So that is the idea of inception designed by Google engineers. The idea is very simple. Instead of going deep and reinforcing the outputs from previous layers, what they did is we'll extract different types of features in the same layer with the different filters. So we'll have a 1x1 convolution on direct input. Then after 1x1, 3x3 convolution, again 5x5. Then just pool that and do the 1x1 convolution. Pooling again the what do you call the size of the matrix will reduce, and then use that, and then add all those things. Means in the sense here, concatenate all those things. You will have a rich feature base in every layer. So that is what they thought. Instead of going with only one type of filter, previously they used to go with only one type of filter in each layer, either 3x3, 5x5, or something like that. Anything the user selects. But the Google has thought, okay, we'll insert more features in each layer. So that is what they thought, and they came up with this idea, and it is now the top performing model in most of the applications. But you need for training these kind of things, you need a very big GPUs like A100s that are available only in servers from NVIDIA. Now you can just see here. At the same thing, I try to put it in a different way. So how many layers we have, And the number of parameters also with each layer, the number of parameters will go up exponentially. That's one thing we have to keep in mind. And more parameters, more training time, and if it is really required for a application, then we can go for this. Now, how computers see this stuff, you all know how computers see, but to understand what exactly goes on inside CNN, we have to just see. So how computers see, this is on my nose. Now it sees only numbers. So these all these things that we see with our usual eyes, the computer see it in the form of numbers, coded numbers. Actually, it is showing numbers. Each number is a color code. You can see the black and the bright areas, how it is showing. Now for color image, we have three components, RGB. So we have to take care of all the three. We have three matrices. Now in case of gray images, we'll have only one matrix. But in case of color image, we'll have three matrices. So how this to be transferred to my deep network? So what are the features it will extract? So can just for doing small things, we'll can just see the representation, because the point is when we are applying anything like images or some kind of data to the models, like impedance matching in electrical engineering. For any circuit engineering branch, people will know impedance matching for maximum transfer. Here also, the matrices size should match for transferring the values from input to the into the network, into the model. So that's the reason why we have to focus on that. You can just see it shows only numbers. So what is the difference between classification and regression? You can just see here. So classification, it divides into two parts, any kind of data. So, and the output is always represented in probabilities, which they're showing that this particular red dot belongs to a particular class with this probability. So that is what the classification does. The outputs of a classifier are always probability values. So I'm just going back only to show the difference that is there between deep learning and machine learning. So you can see for machine learning, we have to sit and extract features. And the last few layers, the dense layers, the people will call them as dense layers, are same, because those are the components that are learning actually. The remaining, okay, the convolution layers, they extract features, but still those features extraction process is also learned based on the learning that is happening in the final layers. So you can just see. So the other difference is the supervised learning models that we are proposing. We are seeing just are for classification. So if you want to do for unsupervised, it will be for clustering. So the clustering, can just see, doesn't require any labels. So CNNs, we cannot do so. These are the components of making a deep learning model. So we have made some of the models, our database creation. So basically we used it for skeletal human action recognition most of the time. So we have feature extractions, and because the setup will give so much of data, it's very difficult to handle by the system. So we have to convert those into features, because the actions are varying in both space and time. So that is a big constraint. So we have to handle both those things. So we extract a spatio-temporal model for feature representation. And then we apply different deep learning models that we, again, as you can see, and the classification is always a score, probability score. And these are the labels, and each label will get a probability. So, and if you add all the labels, we'll get one. Now we'll see a small example here. So, fruit classification with machine learning. You can just see I have 5 fruits to make it very simple. So I'm not going with large data. So we have 5. So we have to, this is how actually the computers see. You can just see. And I can just see the difference between the last one. Maybe it's a pear, I don't know. And then the apple, the values are almost, means because they're in red color, they have similar values. If you extract the features, and these feature extraction algorithms, they call it as handcrafted features. So they convert the pixels into numbers representing different colors, shapes, or texture, whatever you want to select. There are different algorithms for that. Now I just did a small one to show you. So this is wavelet transform in 2 layers, in 2 levels. You can just see the collection of these the pixel values in these layers are because wavelet transform also does the max pooling operation. So we can collect the small data. So you can see here the features. So the images are represented in terms of some values. I can say both are almost same. So that is the biggest problem when we extract features. And so the feature extraction algorithm should be very precise so that there should be between classes, the features should be very much discriminative. So that is what is required. And if the algorithm is not performing well, then it's a big loss to the means it affects the performance of the machine. That is the problem. So if I use directly all the pixels, then you can say why you extract features, because both the features are looking there's a small difference is there, but that small difference is has to be transferred to the machine to learn. So that is the big problem, because at the end of the line or the all the features, all what we are talking, we are giving English names. The system looks at them and says all these are numbers to me. So if the numbers are not very far, it's very difficult to for the system to learn to discriminate between these feature values between classes. So if you can say, I can take all the pixels and I can see the size. Here the size is very small. I have only 250 values here, and see 3 into 10 power 4 pixels I have to give as input to the system. So that is one thing which we can avoid by extracting features. Now, the problem with the machine learning algorithms is you can just see there are two major problems. One is you need to tell the system what is unique about your data. So it's for identifying that whatever data you are giving to classify that into a particular class, you have to tell it these features are unique to your class only. So that is big challenge. That is big challenge because there are so many things that happen in between from the original thing to the devices that you use for extracting, like to capturing the data. For example, you use like you have an Apple phone and a Samsung M series phone. You take the photograph in different lighting, same lighting conditions, you'll get two different values in the pixels when you load those two data into of the same thing, of the same, let us say, face image. So that is what happens with the that is why people thought we'll do the feature extraction things automatically. So now the biggest problem, so once you extract the features, because again they are again big in number, so what are the key features that are contributing for my algorithm, for my machine learning algorithm to perform at its peaks? So that is what is the big challenge. There's two challenges in machine learning. Now that's why I thought they invented deep learning models. And I can see for face they used to map. Now also they are mapping. Recently Google has released their face map, which has around 60 or 80 points on the face for face recognition. Now that is the big challenge here. Now the deep learning, what it does is it says that we are extracting features hierarchically. The deep learning, if it is talking to you, it will tell you that I'm extracting different set of features with different characteristics at different stages of my training. That is what deep learning is saying. If you have a pattern like this, and in stage one, it will see only a small portion of that, and then in stage two, it's like a little big portion. Stage three, it increases. At stage four, it sees the complete object. So it reconstructs the complete object. That is what the deep learning models will say, and that is what they are doing. So if you want to believe that, it's okay, but we'll see, and we'll see how it is correct or not. So coming to images, the first layer will extract the edges, the small portions, and then the second layers will do object parts, and third layer will extract the entire objects. So that is what the idea says, the deep learning. So, but we have to check whether it is doing the same thing or not. So we starting, this is a simple model. If you are interested to do this, so many people have done for apple, mangoes, and other stuff. Now, the problem with this is to extract the visual features. It's good, it's a mango, but in the image where the mango is sitting is one big challenge for the machine to identify. It can identify it's a mango. Suppose that mango position shifts. You are capturing a different image. That's why the training data should be large. So that is the spatial location of the object also plays a major role in detecting the images. So that is not possible with machine learning. So for doing that, you have to again go for either particle filter or Kalman filter to track the position of the object in the image. So that thing is handled exceptionally well by deep learning models. So let us see how it does, how it remembers the spatial location of the object. So this is my dense network. This is my previous ANNs, where there are so many neurons which will learn. Now, what's wrong with this feature extraction? This same image, my photo only, and you can see my size of my face, which is varying differently in different photos. Now, if I give this kind of input to my machine learning algorithm, even though I extract features very well, my feature extraction algorithm is very good. The problem is the location of the face or the object in the image, which varies continuously. So that is the big challenge. So that is the big challenge, and how to do that. The machine learning, all the machine learning algorithms, they use again the background subtraction to extract the face, location of the face using Kalman filter. or the, because they're very good trackers. Till now, the Kalman filter or the particle filter are the very good trackers. Previously, before these things were there, people used to, like up to 2013, they used to use Kalman or particle filter for tracking objects in the image. Now, it transformed everything with this. Location of object in space. So that is what is exceptionally well handled by our filters. Now, if I see, I just done feature extraction. Most popular feature extraction models I have applied on different images. There are three. The first one is HOG, histogram of oriented gradients. And the second one is the Swift features, scale invariant feature transform, and the third one is surf features. And you can see the different, how it perform. I can just see the size of feature vector for 2D, because the image is 256 cross 256 cross 3. So then, and the points, you can just see the feature vector points. It's a vector. So you can just see, mark them. So you can see the points. The idea is to transform the 2D tensor. The matrix is called as tensor by Google people, and it has become a standard. So you can just see here, transform those 2D image into a 1D tensor. So that is the job of feature extraction. That is what we are going to do with the same thing. With the deep learning also, we'll transfer the 2D image into a 1D tensor. Now, once we do that, and we can train our normal neural network or any classifier. You can use SVM classifier, you can use the Bayesian classifier, or you can use anything. But most unfortunate is that there is the spatial information was missing in all the, even this, it's not present at the feature extraction stage. So for that, we have to do like, we have to include the tracker, Kalman filter tracker, or other trackers. So that is big thing, and you can see there are too many parameters, too many features that are, some are unwanted, some are wanted. What are the key features? There's so many algorithms were proposed previously, prior to 2012, 2010. It was the research field was very active, and how to extract the key features. At the time, the most of the research was to find a feature extraction model. So like HOG was developed around 2010, Swift, Surf. There's so many features that came into existence at that point of time. Now, this for one image, it's okay. But if you do for like a video, it becomes really unnatural. So the point is, what they thought is how to embed the spatial information into the neural network. So that's where the concept of convolution, because convolution does the same thing. So what is exactly the convolution operation doing? On a 2D patch, it just give a small 3x3 patch of small matrix. Select that matrix randomly, because we are learning the features. We don't want to, because in what do you call, in traditional feature extraction algorithms, we'll propose a 3x3 patch. What should be the contents of that patch? The values, the numbers in the patch, where if you multiply the entire image with that patch continuously, you get good features. So that is what. But here we don't give any numbers to those patches. We'll learn those contents in the patch, the 3x3 patch, or 3x3 filter they call, or kernel they want to call, and we'll transfer the entire information of that patch to a neuron. So the location of that patch or the information about the contents of that patch are stored into the neuron. So that is what that is how spatial information is extracted. So this is how it goes. The first layer, not layer, this is the first operation, second operation. So that is in the first layer. The entire operation goes, let us assume, in the first layer. Now the point is how can these patches be weighed to detect particular features. So you just have to slide the window. So what it is actually learning, let me go back. Yeah, these are the weights attached to those neurons are what is being learned, and the contents of the filter are modified according to those weights. So that is the idea behind, that is the operation that happens in the convolution layers. So you can just see. So that's why the name, yeah, you can get that. So it shifts. So again, the weights are here in this case a set of filter values that are local to that particular patch. So that is that patch. All the patches are again learned by the system. So that's why where the actual learning happens in the convolution layers, and they preserve because they know what is there inside, on what in which part of the image they were applied. So all that, because you cannot do this operation just like that. So each patch will have a numbering. So indexing will be there. So in that process, the entire spatial structure of the object in the image is preserved. That is the big thing, the big evolution that transformed people to use convolution neural networks compared to the traditional machine learning algorithms. Now, I want to just again, still, I have that doubt. Is it really doing that same thing or not? You can see here 2x, both can recognize as X, but can computers do the same thing? So that is the big question. So because that is how the data is, this is the first left-hand side of your screen as it's an exact training image that is provided to you. But in real, the test image or the inferencing image will be like this. You can just see, and it is same. For human being, it is quite simple to recognize that as X. Can the computers, can your deep learning model do the same thing? So that is now for a computer. So if you say window shopping, for human beings, we can understand what exactly is window shopping. For a computer, it is shopping for windows. So that is the difference. Now I just applied a patch on that, and I try to why patch processing or why filtering works actually. So you can just see here to show you why it actually, because why we select uh, uh, different size of patches, because some patches will do 3 by 3, 2 by 2, 5 by 5. You can select anything. So that is why convolution operation works very well. I use 3 by 3, and if you want to use different size of filters also, you are welcome. So here at this stage, I think we understood the concept of convolution. It preserves the spatial structure of the information in the image or in a spatial dimension. So if the data is both is spatially represented, then CNNs are the models to for anybody to operate on. Just to pressurize your biological neurons is the basic convolution operation that was used. Just because most of you know how convolution works. I just kept this. Sorry for my ignorance. Now, 2D convolution, is it really preserving the spatial structure. I just operated on this, how it does the 2D convolution part. Just add and so this figure you might have seen so many times how convolution operation works. But here the only thing is the size reduces by 2 pixels. And this is a 5 by 5 image. It has gone to 3 by 3. So every layer of convolution operation reduces the size of the image by 2 pixels. If you don't want that in your program, you can just write that also. You can add zeros, 2 pixel zeros in each side. You can, or you can interpolate the edges of the image, because we don't do that because the edges doesn't have any information most of the time. So we avoid doing that. You all know why we go for always 3 by the odd number of filter sizes. So for not losing the borders, just add additional pixel layers and then do the padding and then operate that. So you will not lose the border information, but we don't do it because it's because there is most of the data we operate on doesn't have useful information on the edges. So that's why we seldom use that kind of padding or something if you want. Now, what exactly we get from the filter? Now you can just take all the 3 planes we operate on that. We operated with already existing filter models. Like there are so many image filters, Sobel filter or Privet or something, Canny operator, so all that. And you can just see this is how it looks. Now you can explore that on your with OpenCV in Python. We did it in Python. And these filters are already predefined filters, like the weights or the values. You can just see the values of the filter which are there inside. They have predicted those values, or they have attained those values through some mathematical modeling. So that is what they have done. You can just see the input image, the pixel values, how they have changed. Yeah, the negative numbers, it takes it as a 0 black pixel. The white values will be preserved. Now, how actually this is happening? Once we'll transform what we have learned till now into a complete convolution model. So we operate convolution network, convolution filters, and then we'll introduce the activation function value most probably, and we'll do the pooling operation, and we'll try. Now, what is there happening in the convolution layers? We know that you have already seen. So that is the weight vector for each input. So here we are taking 3 by 3. You can take any filter. So you can just see here, I've done a small kind of 3D animation to show you. So once the filter is moving, the transformation from that patch, the information that 3 by 3 patch is transferred to this neuron, the single neuron. Again, the neuron. So this is volume is created. So once the problem is when you say 28 cross 28 cross 3, it's a 3 is for all the 3 color image, 3 planes. And we need an extra dimension. That is, we have to add an extra dimension to save the volume of filters that are coming out of the convolution layer. Now the filter movement, you can also specify that. That is again a hyperparameter. How many jumps you want from one spatial location on the image to the other. So you can, it's called stride, and it will be around 1 or 2 or 3, your choice based on your application. The stride 1 will transform, they will move the filter on the pixels by 1 pixel. 2 will do it by 2 pixels. 3 will do it by 3 pixels. So that is how it goes. And the output of the convolution layer again is I can just see is the filters, and each location is called there are different terms. So it's a receptive field, the yellow patch, and it will be transformed into an image. So each patch will each filter will get an image in the output. So if I use 50 filters, assume so 28 cross 28 cross 3 cross 50. So we have 50 images in the output. So that is the dimension of the total number of filters. So output is output of the convolution layer is a 4D tensor. So always before the convolution operation, the output means it is defined as the extra dimension is given to the uh, output of convolution layers, where it can save that extra dimension to get a 4D tensor. So here there are 16 filters. So the size of the matrix will be 28 cross 28 cross 3 into 16. So we have 16 dimension 4D tensor. Now, once we have done that, we will apply the activation function. You can just see this is the feature map extracted from the convolution layers and the ReLU operation performed on that. So what exactly the ReLU is doing? So it will transform all the positive values as it is in a linear way, and the negative values it will make it 0. So I can show you. This is my feature outputs. You can see. Concentrate on the top left corner. So this is my feature matrix, and let us apply ReLU on that, and you can see. So you can just see here, minus 558 in the first one is transformed to 0. So all the negative values will go to 0, positive values will remain as these. And the meaning is it's quite linear, means it will transform all the positive values from the input to the output without any deviation. And for all the negative values, it will put to 0. So there are different activation functions. You can use them. So this is the ReLU activation function. Now, basically the idea is to again to introduce nonlinearity into the entire learning process, and transfer the data, to fire the neuron for the data to transfer from input to the output. So that is the basic operation on these things. But only you can design your own activation function, provided it has to because the entire process is a mathematical, really intensive process. So that whatever activation function you are designing, it should follow the simple rule of linear algebra, that when it has to be divisible. Only thing that is the only constraint on that. So it can be differentiated. It has to be differentiated. Now coming to max pooling, you can just see. So it will reduce the size. If I use a 2 cross 2 filter, it will reduce the size by half. If you can use 3 cross 3, you can use 4 cross 4, your choice. 1 cross 1, there is no point of using that. So this is my ReLU output. On ReLU output, we use max pooling of stride 2. So what changed? Nothing changed. Yeah, it changed. You can see the difference in the image, but we made it to look like they're same. Both are different. Both have different resolutions. I can show you. Just focus on the top right corner, sorry, left corner, where 0, 0, 9, 11. So if I use a 2 by 2 max pooling on that, I will extract the number 11. So you can see, just you can extract the number 11. All other pixels are gone. Why zeros are repeating? Because all 4 zeros will extract zeros. So you can see can do max pooling of 2. So you can do average pooling. You can do a lot of other poolings also. Average pooling, take the average of all the 4 numbers and put it in the single box. So you can just see the difference here of different average pooling on different strides, like stride 2, stride 3, stride 4. So stride 4 will, now this is the average pooling when we applied on the same image set. I can see when I apply average pooling, we'll have, we'll reduce the size of the data. So for stride 2, it is 128. For stride 3, it is 86. 4, it is 64. So your choice for a particular application that you are designing, which one is good. So you can select different types of pooling mechanisms also. There is stochastic pooling also, probability based, but all these most widely used is the simple one. So most of them use that. Now, once you do all these things, the final layer will have a single feature vector, which you will train using the regular dense layers. Now, for anybody, if we was starting up or is in the early stages of learning, the most errors that pop up during a training program or during coding process is the strides in convolution. Now, if you give improper image sizes and you ask the convolution operation, so it gives most of the time it throws up the error, even for a very good programmer also. Because if you take 128 cross 128 and you don't control the strides properly or the convolution filters properly, there is a chance that it will do the math operation and it will throw the errors. So that is what happens. And strides in pooling, the size of the image, and padding during convolution. And if it is a image type, it's a grayscale or a color image, all these. And the number of convolution layers you choose, like you choose for a very small image, you give a very deep network. Unfortunately, the size of the matrix becomes 0 at the end of, suppose you give 5 convolution layers and you take a very small image of 32 cross 32. And by the time it reaches the 5th layer, the matrix vanishes because of max pooling operation. So every time it reduces by half. So 32 becomes 16, 16 becomes 8, 8 becomes 4 in the 4th layer. And then after that, it just vanishes. So that is a big problem. And the selection of activation functions is also a key role. And you can, what we gain from all this, so we understood that spatial invariance is preserved after pooling. So, and at the same time, it reduces the dimensionality of the entire data. Now, the question which I was talking is each layer. So if you type these things, convolution neural network in Google and ask for it to get you some images of the CNNs, the basic ones, they'll show like this. So the layer 1, layer 2, layer 3, are these really, the intermediate layers are doing the same operation or not? So how can we really go deep and see that? So let me go deep and show you. This is my intermediate layer output from the first layer. After the first layer, I got this because I'm seeing. Am I seeing the edges here? I have the entire image. But the point is, they're also doing the same thing. The same output is here shown here because it gives out the entire output, but it is only trying to focus on edges. So, but in reality, we will not get images like this. It's only for representation that the CNNs are learning features in a hierarchical way, hierarchical step-by-step process. So first layers will do that. This is my second layer. And the third layer, you can just see it's focusing on the entire area, which is very important for the object. Now, once we touch the final layers, the outputs will be like this. So that is how the intermediate layers outputs can be extracted. Now this is the basic thing which we have already seen. So what happens inside that? So if you want to operate, so just focus on the parameters, the hyperparameters of the network, which you have, which are in your control, and the learning parameters of any network are either weights or biases. So only the first part is only feature learning, and the second part is where the dense layers is where the entire operation is happening, where it is actually learning to predict the things that are there in the images. So that is the two parts of the network. There is a fully connected layer. Now we'll come to fully connected layer where each neuron is trained with the objective function, with the activation function, weight matrix into X plus B. The same, the linear algebra expression is valid everywhere. So this is to show you a simple example how we have done it on different images. But this network is not suitable for doing video. It learns from the images. We have to train more if we want to use it as for inferencing on a video. I just show you what happens, how each layer learns. The first top image we have already seen. The second one, what are the different features that are being learned. Now we have so many sites which are giving these kind of examples. What are these? What is the stuff in the inner layers, and how each layer is looking at the input image. Now, networks that were very successful, which we have already seen. So, but the scale of layers, I want to show you the scale of layers, how they increased it over a period of time, over the period of time in last 4 or 5 years. So, as I pointed, AlexNet was first introduced with only 8 layers. Then it's a second version of AlexNet that is called ZF from the same lab. Then VGG came into existence. Then Google has done its own with 22 layers. ResNet 152. Now they go beyond that. So they go for thousands of layers, and they train around on hundreds of GPUs in cloud environment. So these are the models previously. I can just see here in 1998, the first, it was trained on CPUs, 10 transistors per chip, and then in 2012, so it was transformed to 10^9. And as you can see, the number of parameters are huge. These are the different networks that you can try. Yeah, batch normalization is one layer that is added in last 3-4 years. for the regular networks. It means you take so each batch contains suppose 32 images. So each image is different. So each image has different values. So normalizing all the values to a particular set of values is very important. So batch normalization has done wonders to these deep learning models, which unfortunately I have skipped somehow. So thank you very much. And any questions from anything you want to know, I'm happy to answer. So I suppose hope you understood everything, or and thank you for patient listening.
Sir, excuse me, sir.
Yes, yes, sir.
Sir, I want to know, sir, what do you mean by the training of the machine? Please explain in simple way, sir. Please.
Sir, I couldn't get you, sir. What exactly?
Sir, no, sir. Suppose that you tell that I'm just making an algorithm or a machine which checking purpose train the system, training the system, sir. Training. What do you mean by the training?
Training is like we are teaching the network to learn the particular things. So tomorrow morning, can I show you? Tomorrow morning we'll have a hands-on session where I'll
Okay,
take a
sir.
small network and I'll show how. In the sense, speaking roughly, training is uh, designing the weight matrix and the bias matrix. That is what is training. What we understand by training. But tomorrow I'll show you, sir, what exactly I'm talking of training.
Okay, sir.
Yeah.
Okay, sir. Okay, sir. Thank you.
So thank you very much, and we'll see you tomorrow.
Any questions that anybody is having? Okay, sir. Thank you very much. We are going to close the session for today. Thank you very much for joining the session.